purpose of today's show is to gain a better understanding of a very controversial subject, and that is cold fusion. Some believe this topic is dead. However, my guest, Dr. Eugene Mallove, will not let it die. He believes passionately in the viability of cold fusion. In the simplest terms, cold fusion uses water to produce energy at room temperature. Some things we're going to look at today are why cold fusion has not been embraced by the scientific community, the politics involved, and what the implications would be if cold fusion were proven scientifically. Let me first tell you about Eugene Mallove. He holds a science doctorate in environmental health sciences from Harvard and advanced degrees in aeronautical and astronautical engineering from MIT. Dr. Mallove is the author of several books and has been a science writer for many magazines and newspapers. His 1991 book, Fire from Ice, Searching for the Truth Behind the Cold Fusion Furor, was nominated for a Pulitzer Prize. Currently, he's editor-in-chief of Infinite Energy magazine. He served as technical advisor to the 1997 movie, The Saint. Welcome to the show, and thank you for coming.
Oh, delighted to be on.
If you would briefly tell us about the 1989 experiment by the scientists at the University of Utah, to just kind of give us a background as to how this whole thing started.
Yes, there was an amazing announcement at the University of Utah in 1989 on March 23rd, just before the Exxon Valdez ran aground, ironically. Doctors Pons and Fleischmann at the University of Utah announced that they had a little cell which was using a special form of water that's in all water. It's in fact called heavy water. 1 out of every 6,500 water molecules is heavy. Okay, it has heavy hydrogen in it. And they said, look, we pass a current through this cell, and it has palladium electrodes and a palladium electrode and another electrode, pass electricity through it. They said we get much more heat out of this cell than can be accounted for by any known ordinary chemical reaction. It must be nuclear, and we believe it may be fusion, akin to what is going on inside the stars, but not with lethal radiation.
Okay. Let's start out with some of the basics, and they are very elementary if you have a science background. Okay, first you have the atom.
Yes.
Okay, the atoms make up molecules, molecules make up matter. All right, so far?
Molecules are matter,
Okay.
atoms are matter, yes.
All right. Now, the atom is made up of electrons with neutrons and protons in the nucleus.
Right. The nucleus is very tiny. If the nucleus of an atom, any atom you want to pick, is the size of a pea, then the outside of the atom, the electrons flitting about, very light particles, would be the size of a football stadium. So we're mostly all space, and our nuclei are very tiny within each atom. If you could blow up an atom to the size of a football stadium, that's the scale it would be.
Okay. One other minor point, not minor, but one other basic point. Chemistry involves the manipulation of the electrons.
Yes.
Nuclear physics involves the manipulation of the neutrons and protons.
In the nucleus.
In the nucleus.
That's correct.
Those two sciences don't overlap.
That's right.
Is that right?
In other words, when you do ordinary chemical reactions like burn a match or light a cigarette or burn oil in your oil burner or coal in a fuel plant, you are doing chemical reactions. All the atoms, as far as science knew up to Pons and Fleischmann's time, all the atoms never change. The only way you can change the identity of an atom, for example, hydrogen into helium, like the sun does, is to have very, very high temperatures, hundreds of millions of degrees, 20 million degrees, what have you, or in large, fantastic accelerators that cost billions of dollars. The idea that at ordinary temperatures, or even hundreds of degrees or 1,000 degrees, any atom should ever change is unthinkable by modern physics.
Okay. You have fusion, which is you take two hydrogen atoms, fuse them into helium, releasing energy. I'm just going to go through two more basic points here. That is the differentiation between cold fusion and hot fusion. Cold fusion uses chemistry to fuse the nucleus at room temperature.
Okay, let's start with some basic ideas here. Ordinary hot fusion, like the sun does, or like what the people at Princeton University and their tokamak reactor do, they create hundreds of millions of degrees, or in the case of the sun, only 20 million degrees.
They use
in the core.
lasers, right?
Sometimes they use lasers, but at Princeton they use high magnetic fields and electric currents and so forth to squeeze the atoms into a frenzy so that the positive charges of the nuclei don't have as much effect anymore, and basically you get close enough, the positive charges of different atoms, like hydrogens, get close enough and they can fuse and create a new element, like helium. That's hot fusion.
Okay.
Now, cold fusion is just a name, and it was given as a complicated historical fact as to how that arose. But it does come certainly because Pons and Fleischmann in 1989 were telling the world that they could do the equivalent of making energy without dangerous radiation. They could change elements, because they thought they had evidence of that, in a little cell, in a cell like this, a cold fusion cell, this experimental one, for example. They said they could do it. This was very radical, still is, by those who aren't looking at the evidence. But the bottom line from Pons and Fleischmann was this: out comes heat, which we want, and energy for use, and generating electricity and hot water and so forth, not deadly radiation. Moreover, much more energy coming out than any chemical reaction could possibly explain.
Okay, so they cause the nucleus to fuse at room temperature.
They cause some change in the nuclei.
All right.
Those changes are very complicated,
All right.
still controversial, even within the cold fusion research community.
All right, let's look at some of the problems with cold fusion.
Yes.
I guess you could start out, one of the problems, as I understand it, is that in order to prove something scientifically, you have to do it over and over again in order to get the same results. And this has not been true with cold fusion experiments?
That was true in the beginning. There were difficulties. In fact, Pons and Fleischmann happened to pick, since they were brilliant scientists, they happened to pick the most difficult of the cold fusion systems now. This is heavy water. That's what they started with. And they had a palladium electrode, a special metal. When they packed the deuterons, the nuclei of this heavy hydrogen, into the palladium, they got this excess heat. And others also got the excess heat. But it wouldn't come always on a regular basis. It would be sporadic. We now know that it's a very severe problem of this system having to do with the nature of the palladium. The scientists who did what I would call a hit-and-run job on cold fusion in 1989, they looked at the sporadic evidence, they looked at the difficulties at the time, and because many of them in this federal panel that looked at it had definitely a preconceived notion, their admission now is they had a preconceived notion, so of course they came to reject it very quickly. But the evidence now, I must tell you, is beyond doubt. Not only is it beyond doubt, and in many instances fully reproducible in systems, particularly those that use ordinary water. There are now systems that use nickel electrodes, not palladium, and every single time you get excess heat of a massive nature.
What then is with Japan and them closing their
new hydrogen energy program.
Their research of cold fusion,
Yes.
MITI?
The Japanese Ministry of International Ministry of Trade and Industry set up a very highfalutin program.
And they recently closed it.
And they recently said they were going to close it down. It's still doing the
Okay.
research there. They had what we call a lot of bricks and mortar, much as the hot fusion people have. Huge buildings, huge devices, huge bureaucratic programs. In this case, they bought lots of equipment. They started reinventing the wheel, as Japan often does. We, in our magazine, Infinite Energy, warned about 5 or 6 months ago that the incompetence level of certain scientists dragged in at the last minute who were working there was very, very bad. So, yes, Japan has formally closed its program, but that has absolutely nothing to do with whether or not cold fusion is real. Just as any given, say, competitor in a car industry or the aircraft industry may have problems with the particular technology they're pursuing, of course, yes, they had problems.